Numbers are the bedrock of our understanding. They describe the vast distances between galaxies and the intricate workings of atoms. We use numbers to build skyscrapers, to send rockets into space, and to track the delicate balance of life on Earth. But what happens when the very tools we use to understand the universe are themselves imperfect? In the digital realm, where computers reign supreme, we encounter a peculiar challenge, representing the infinite tapestry of numbers within the finite confines of a machine. This is where floating-point math enters the picture, a system designed to capture the essence of numbers, both large and small, within the digital landscape. Imagine a vast cosmic ocean, its depths teeming with an uncountable number of stars. Floating-point math is akin to casting a net into this ocean, capturing a representative sample of these stars to study and understand the universe as a whole. It's a powerful tool, but one that comes with its own set of limitations. Just as a fisherman's net can only hold so many fish, floating-point numbers can only represent a finite subset of all possible numbers. This limitation arises from the very nature of computers, which rely on discrete bits of information to represent continuous quantities. At the heart of floating-point math lies a clever compromise. Instead of trying to represent every single digit of a number, which would be an impossible task for very large or very small numbers, floating-point representation focuses on capturing the most significant digits and their relative position. Picture a dancer gracefully gliding across a stage. We don't need to track every minute movement of their body to appreciate the beauty and elegance of their performance. Similarly, floating-point math captures the essence of a number by representing its most important digits and its order of magnitude. This is achieved by dividing a floating-point number into two parts, the significand and the exponent. The significand represents the significant digits of the number, while the exponent indicates the scale or magnitude. Think of it as writing a number in scientific notation, like 6.022 times 10 to the power of 23, where 6.022 is the significand and 23 is the exponent. This elegant solution allows computers to represent an incredibly wide range of numbers, from the unimaginably small to the astronomically large. However, this efficiency comes at a cost. By sacrificing some precision in the representation, floating-point math introduces the possibility of errors. In the pristine world of mathematics, certain truths are considered absolute. 1 plus 1 will always equal 2. The order of operations is inviolable, but in the realm of computing, these fundamental truths can sometimes become a little fuzzy. Floating-point math, for all its ingenuity, can lead to unexpected results when calculations are performed. These errors arise because the computer must round numbers to fit them into the finite space allotted for floating-point representation. Imagine trying to squeeze an infinitely long decimal into a box with a limited number of slots. One common type of error is rounding error. This occurs when a number with an infinite decimal representation, such as 1/3, is rounded to the nearest representable floating-point number. The result is a tiny discrepancy between the actual value and the computed value, a discrepancy that can accumulate over multiple calculations. Another type of error is cancellation error, which occurs when two nearly equal numbers are subtracted. The subtraction can magnify the rounding errors present in each number, leading to a significant loss of precision in the final result. Section 4. The price of imprecision. While these errors may seem insignificant at first glance, they can have real-world consequences. In finance, where even the smallest rounding error can compound into millions of dollars, floating-point errors can wreak havoc on financial models and trading algorithms. In scientific computing, where simulations and models rely on highly precise calculations, floating-point errors can lead to inaccurate results, potentially skewing research findings and hindering scientific progress. Consider the story of the Patriot missile defense system, which during the Gulf War failed to intercept an incoming Scud missile due to a software error related to floating-point arithmetic. The error, which involved the accumulation of rounding errors over time, resulted in a tragic loss of life. This incident serves as a stark reminder that even seemingly minor computational errors can have far-reaching consequences, especially in critical systems where accuracy is paramount. Section 5. Taming the floating point beast. The good news is that while we cannot completely eliminate floating point errors, we can take steps to manage and mitigate their impact. By understanding the nuances of floating point math, programmers can make informed decisions about how to represent numbers, perform calculations, and handle potential errors. One approach is to use higher precision data types, which allocate more bits to represent numbers, reducing the impact of rounding errors. However, this comes at the cost of increased memory usage and slower computation times. Another technique is to carefully order operations to minimize the accumulation of rounding errors. For example, by adding small numbers together before adding larger numbers, we can reduce the likelihood of losing significant digits. Programming languages like R and Python offer built-in functions and libraries to help developers work with floating point numbers more effectively. These tools provide greater control over rounding modes, allow for interval arithmetic, and offer ways to check for and handle potential errors.